chat to finding it because like I found the point and then I don't know. I was just gonna use the mapping rule and it just didn't work because it doesn't make sense.
Okay, so the kind of I'm gonna I don't know why that didn't pull. What's going on? We hear ours. Uh, where was I? Over. Come on. What? Why did that move from there? You silly thing. I have no idea what just happened. Yeah, you guys can see my screen. Or I could have just done the smart thing and just straight up opened the file. Hmm. Well, we'll open it here. So once it gets down to where it needs to be, I can make that a little bit bigger. So this kind of purplish one, that's just the regular square root of x. That's what's being transformed. So to me, it's pointing the opposite direction and upside down, so there's some sort of reflection is the first thing. The endpoint is fairly easy to find. Um, then you have to look at it like this is up 1 over 1 is a horizontal or vertical stretch. Personally, I'm going to go up 1 and over 2. So if I've gone, instead of going up 1 over 1, I'm going, well, down and over 2. Does that have a horizontal stretch? That one there, I would look at visually as a horizontal stretch. You don't actually have to do it algebraically. That has a horizontal stretch of a particular number. Instead of 1, it's something. Up 1 over 1, up 1 over 3. Well, the next one is 3, 1, and then 1, 2, 3, 4, 5, 6. So that should kind of help. Does that help a little bit?
Yeah, a little bit. Thank you.
Okay. But you can do the stretch parts algebraically, or you can do them visually if you have the graph. So if you have the graph, I would do the visual kind of idea. Where am I going? Oh, there we go. Oh, we got all sorts of fun people here today. And that hooligan Aiden. You guys are so quiet. So unlike some of you in class. But it's 10:03. So yeah, today's Thursday. Monday is a holiday, so we're not going to meet Monday, but I'll be here tomorrow and we'll do some more stuff. We looked at some word problems in fitting, finding a horizontal or vertical stretch, a horizontal asymptote if there's a transfer or translation, and we did kind of that sort of stuff. The same thing with this one. What's the temperature after an hour is fine. How long does it take the temperature to get to 50 degrees? Well, you can estimate it on the graph, but because your variable is in an exponent, this gets a little tricky. We talked about it more with Mr. Bellier's genius virus. To get 1,000 people infected, well, that's our y value. And we divide by 10, we have this 2 to the power of x over 8. Well, that gets to be a bit of a problem because we, at this point, well, you can't multiply by 8 because that's part of an exponent. To get the exponent out of, or the variable out of the exponent, we need to use the inverse of an exponential function, which is something called logarithms. It's actually a relatively new bit of math. It's in themes. I put it up early this morning in RF8. is about introducing logarithms, and we're going to do a bunch of different things with them. So this is where this file is. I don't know how many pages it is. We'll see how much we get done today. Logarithms, unfortunately, a lot of people find them confusing and perplexing. But fundamentally, if you can square something and take the square root of something, if you can raise something to a power, a logarithm is the inverse of that. It's just like a square root because it deals with exponents. And when we started exponential functions, we went back through all of those exponent rules um, from grade 9 and 10. These have their own sets of rules, and they're all, you can derive them all from taking the inverse. So a logarithmic function or doing a logarithm is the inverse of an exponential function. That's all it is. They can come in super handy. There's a whole section of calculus called I think it's logarithmic differentiation, where if you take the logarithm of everything, it actually simplifies things. So we've done exponential functions. Y equals some base to the power of x. If I do the inverse, when we do the inverse, we, as a mapping rule, just to kind of link it to that, we change the x and the y. When we do y equals x squared, the inverse of that is x equals y squared. We take the square root of both sides, so we get y equals this, not the square root of 3. I have no idea why I got a 3 there. Y equals the square root of x. So if I take the inverse of this, we would have x equals b, because the base doesn't change, to the power of y. So there's our inverse, but that doesn't really help us a whole lot. So we write these as what's called a logarithm. I think it was an English guy named John Napier who actually came up with the idea of writing these as what we're going to. And these two kind of lines, I've covered them up because I like to write things, are equivalent. Um, y equals log base b of x. So this is what we call the exponential form. This is the logarithm form. Now I need to move some arrows. Order. No, not to the back. Sorry. Bring to the front. The base is the same as the base here. So if we're talking about an exponential function that is base 2 or base 10 or base whatever, that's our base. It's the same for a logarithm. And once I put that up at the front, I just didn't want to delete things. The x is what's called the argument. So when we take a logarithm, really what we're looking for, like if I link to this, I want to know what that exponent is. So if I take a logarithm, we find what that exponent is. And it's a function. Just like people my parents' age, um, who, I mean, are older than your parents, but sometimes, well, I don't know, my parents, could be your grandparents. Um, if they were doing math, they got trig values. They didn't have calculators back then. My parents are that old. So they had to use tables for trig, and we talked about that when we did trigonometry. Um, you can actually get tables of logarithms, and you can get tables in well, usually two bases. You could look them up and all of that. So we have two stipulations. B has to be bigger than 0 because we can't have we don't have negative bases. B can't equal 1 because if the base is 1, what's 1 to any power? 1. So those are somewhat redundant. So what we're going to look at today, we start with translating these, and we're going to use that kind of relationship. So when you take the log or logarithm of something, what you're getting is this exponent here. So if you have a regular old-fashioned scientific calculator, you have this log button on your calculator. And that log also doesn't have a base. I don't know if I push it. Oh, yeah, you can't take the log of 0 because that doesn't make any sense. 10. Yeah, no, it just says log. So the base, which is the most, there's two common logarithms, which we'll talk about the second one in a minute. But the first one is the log on your calculator is base 10. Why is it base 10? Because we have 10 fingers. That's fundamentally why logarithms are done in base 10. It's also why the metric system is base 10, because we count things in units of 10 because, well, that's what we have. When we did trig, we talked about why it's 360 degrees and all of that. Other civilizations, if we go further back, use different bases. So the value of a logarithm is an exponent. So I did over here, the log of 10 is 1, and we'll talk about why that is. The exponent is placed on the base to give you the argument. So I took the log of 10, and that's base 10 equals 1. So if I translate that back to the exponent form, y becomes the exponent, so the 1 becomes the exponent, the base is 10, and the argument, does 10 equal 10 to the power of 1? So that's what we're going, those two are equivalent. If I take the log, that tells me I need to raise 10 to the first power to get 10 out. So what we need to do is be able to translate. That's all we're looking at here. I don't know why that started doing that. And we'll talk about the natural log or the natural base. So if I have log 2, 8 equals 3, we read this as log base 2 of 8 equals 3. So that's what we're doing. If we want to write this as an exponent, and this is one trick if you want to evaluate a logarithm, well, you can do some exponent stuff and get a little bit of things. I always like to check numbers just to make sure. Hope everybody's doing all right. It's supposed to be nice and sunny today. So the base is 2. The argument is what it equals, and the 3 is the exponent. So 2 to the third power is 8. Log, if I want to know what exponent I raise 2 to get 8, we can figure that out as 3. Now, this is one of the kind of funny things is the calculator has a log button. It's also going to have this one called ln, which I always used to call ln, and then I had calculus teachers who just called it log, and it's like, okay, well, that's super confusing. So we'll refer to it as ln. Those are two bases. Well, we can do base 2 if you're into computers and coding. Well, everything is done in base 2 or base 16, but we can do base 3, base 4, base 5. We can't on a pocket calculator, well, we probably could these days, program all of the bases, but there's tricks around it. So what we're going to start with today, and this is the thing where I'm going to go over. If we were in class, it'd be like, okay, this is your example. Translate those. And because none of you like to unmute, um, the base is 5. The exponent is 2. The argument is 25. 5 squared equals 25. The log base 5 of 25 is 2. The base is 2. The exponent is 6. The argument is 64. 2, 4, 8, 16, 32, 64. I do powers of 2 on my fingers. I look funny, but it works for me. Ooh. The We can have fractions. Can we have a negative? Oh yeah, but that has to do with different things. Uh, the base is 16. The exponent is a half. It's 4. Well, a rational exponent, this means the square root of 16. Well, that we know equals 4, so that works. 4 to the negative 3 equals 1 over 64. Well, 4 to the negative 3 is 1 over 4 cubed, which 4 times 4 is 16. 4 16s is 64. If I ask you on an assignment to rewrite something as an exponential form, it should be correct unless I've made a typo. Like it's not like I'm going to try to do anything. So this, if you see log of something, log of 1,000, log of 43, log of any number, you assume that the base is 10. So this one has a base of 10. The exponent is 3, is 1,000. It's not the same, but it's akin to when we use that radical without an index number, we know that that's a 2 because that's common. That's when you pull up your calculator. We know that's a square root. We know that that's a log base 10. And that's going to come in handy in a number of places. The natural logarithm is the base e. And this is, you'll see on your calculator, ln. So I'm going to just use my calculator to figure this one out. So I have to do this. I need to push 3 and then take the natural logarithm is 1.0986 da 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 da. So this tells me e to the power of 1.0896 da 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 equals 3. And we'll also see this e to the um, x button. E is a number. E is it's an irrational number, similar to our old friend pi. Uh, oh gosh. There's a number of ways to define it. One is a limit, which I'll talk about in 12b or calculus. Um, Pi e, I mean, the square root of 2 is rational as well. I figure out, oh, no, I don't want to do that. Do I clear? 1 e to the 1. E approximately equals 2.71828 71828 718 2818, da, da, da. It goes on forever. It never repeats. It's one of the fundamental constants of the universe. It, it, why it's that number, I don't know. Why is the ratio of the diameter to the circumference of a circle pi? It just works. It's the way our universe evolved, became, however your view of that is. For those of you who like math jokes, well, one of my grade 12 chemistry teachers also taught some of the advanced math, and we were talking about logarithms and all of that in chemistry because they come up in chemistry because you can fit exponential decay to things with e, and it's actually easier to work with. So he said, well, why do we use base 10? I don't know, because we have 10 fingers. Why does the universe use E as a base? And his answer was, well, we as human beings, whenever we are in the grand scheme of things, have 10 fingers, so we use 10. So, well, he said God must have E fingers because E is the number that comes out everywhere in the universe. And I mean, I'm not trying to be blasphemous or anything like that. Where'd my cursor go? Now my technology stopped working because I made not really a joke, but, oh, sorry. So we'll use this a little bit. We'll look at it in some graphs. And, oh, what was I going to say? When it comes to calculus, doing things with E as the base is a lot easier than using the base 10 for a number of reasons. If you take calculus, Mr. Bellier and Mrs. Legier will show you all sorts of fun things that there are some things that just mythically, magically make sense with E. So, what's that? Rewrite in exponential form. Oh, wait. That's kind of what we just did. This is where you would do some, so you can kind of do some of those. Oh, rewrite in logarithmic form. All right, let's look at some of these. So if I want to write this as a logarithm, which is the opposite direction, we know 4 squared equals 16, and I'm not going to be able to do that error. Do I have a single-headed arrow? Of course not. Oh, how about I just use this one? 4 squared equals 16. The logarithm. The base is 4. The argument is 16. The exponent is 2. 4 to what power equals 16? Well, that's 2. The base is 10. The argument is 1/100th. The exponent is -2 because this is 1 over 10 squared, which by our exponent rules is 10 to the -2. There's E. Oh, approximately. Log. Well, the base is 125. The argument is 5. 125 to what power equals 5? That's 1/3. Ooh, E. So now there's two schools of thought. I know some people who write that as log base E, and some people who write that as ln. Um, so those are equivalent. The argument is 148.4 equals 5. That one you can check. Clear 148.4. Take the ln of it. 4.9999 is pretty much 5. So that's this is where if we were in a classroom, I would say, all right, take out your textbook and answer these questions. But we don't have that. Oh God, I just you get better at math by doing practice, but I can't give you 14 days of practice. Scheiße. All right, evaluate each logarithm, properties of logs, and then we'll look at this. So if I ask you to evaluate a logarithm that's not base 10, we have to do some thinking. This is an exponent. So a lot of times, nine to what power equals 81? Well, we know from our multiplication tables, 9 squared equals 81. And this is where we don't really do power. Oh, it's in, I did it in NERF last semester, and I used to do it when I do pre-calc 11. 2 to all sorts of powers, 3 to all sorts of common powers, and you write them out. 4 to some power equals 64. Well, 4 times 4 is 16. 16 times 4 is 64, so I've used 4 3 times, so that equals 3. And we'll do these couple and then call it a day. 3, oops, 3 to a power equals 1 over 27. Well, 27 is 3 cubed, but we have 1 over 27, so this, if I want 1 over 27, we're going to have to change this sign to a negative 3. So log base 3 of 1/27th is negative 3. 3 to the negative 3 equals that. Ooh. 100 to a power equals 10. Well, what's the relationship between 10 and 100? Well, if I square 10, I get 100. So we need an exponent to knock that down. Well, 100 to, oh wait, the square root of 100 equals 10. What exponent does that mean? 100 to the half equals 10. So that's a half. Some of this is number sense and remembering different things. This is a thing on a test and an exam. You would have sections. Do this without a calculator. You need to be able to do that if you're planning on going to university. Check. I'm not 100% sure, but I can't imagine. Actually, it makes it easier on you if your first year calculus is without a calculator, because if it's with a calculator, they can ask you all sorts of things. 5 times log base 2 of 4. Well, a logarithm is effectively an exponent. So when we talk about BEDMAS, I usually say those two are fundamentally the same, and those are the same. So you do those in whatever order they appear. Now, E is for exponents. A logarithm is a type of exponent, so you evaluate this before you multiply by 5. So if I want to do 2 to a power equals 4, well, we know that's 2. So this bit simplifies to 2, and that is 10. Uh, so it's 10:30 tomorrow. I've got something somewhere on. Let's get some more practice sort of things. I will post it. The first bit of it is on. I guess I can open this. Okay, good. Well, that opens. Oh, bye, Madeline. I'll post. Oh, that's graphing exponential functions. That is not what I wanted to. That is not what I opened at all. Oh, there it is. I'll post some of this. Rewrite in logarithmic form. Rewrite in exponential form. You can try those, because these are things that we need to be able to do, and then we'll look at some more of that sort of stuff. I will, I don't know why I closed that. That was stupid. I'll export that and post it. You can take a look at some of that little bit. And that's where we'll stop today, and we'll go over some of that tomorrow, if that sounds okay, before we drop everybody. There was an assignment, I think technically due yesterday. Finish it when you can. I'm not super worried. Is there any questions?
I have a question, but it's about like one of it's about the second assignment.
The second assignment.
The transformation thing.
Oh dear.
Sorry.
Oh no, it's okay. Oh wait, I have. Which question?
7.
7? Okay.
I got like, so I made a map
Yeah.
and then I went to apply it and I got it like 0.6
You got.
for X value.
You got. They all became what?
Well, no, like the coordinate -2 and -1
Yeah.
ended up being 0.6 and -2.
What's your mapping rule?
I don't know if it's right, but
Uh,
-1/3,
mm,
so 1/3x, and then 2.
mm, I would look at your x part. Your y part is fine. But when you have a fraction in an equation for the horizontal stretch, what does it become when it goes to a mapping rule? 1/3 is going to become.
You do the reciprocal,
Yep.
well, does the negative stay, or
Yep.
does
The negative stays, but it's just that number. Okay?
yeah, okay, thanks.
You're welcome. Bye. Adios. We'll see you guys. Well, so I'll see some of you this afternoon for some chemistry fun.